Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 40+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify innovative applications, build skills and standards, and advance partnerships to solve global challenges. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker.
Thank you so much for the opening. A very good day to everyone joining us on Neural Network. Welcome to our Discovery Series webinar. My name is Thomas Bascolo from the ITU, International Telecommunications Union. In today's webinar, we are going to talk about multimodal adaptation of large language models for smart mobility in Africa. As we know, large vision models and large language models have transformed how we approach problem solving across domains. However, when it comes to real-world applications, especially in mobility area or in mobility domain, there is need for models that can go beyond text and leverage rich multimodal signals. For example, GPS data, time series trains, and infrastructure maps. In today's webinar, we are going to explore how we can adapt these powerful models to address transportation challenges specific to African cities. For example, we are going to have examples of cities like Kigali, Nairobi, and Lagos in Africa. From understanding the role of RAG, or Retrieval-Augmented Generation, to designing domain-specific multimodal systems, this session is going to provide insights into building AI that truly understands local urban dynamics. And the speaker today, I'm delighted to introduce our speaker, Associate Professor Ahmed Biabani, who is teaching at Carnegie Mellon University, Africa, and he's teaching courses in AI and digital transformation. His research interests include AI in healthcare, telemedicine. He has also previously worked with startups that uses vehicle-to-vehicle, V2V communication for traffic safety and optimization, but also has initiated collaborative smart mobility lab in Kigali. So he's an academician with deep passion for the academics, and I would like to welcome Professor Ahmed. Welcome and good afternoon or good morning.
Good morning. Thank you, Thomas, and thank you for the whole team for inviting me. I'm very glad to be here, and I hope that we can go away from this talk with some good ideas on mobility in Africa. I'm going to start sharing my screen, and I will put it into presentation modes. Okay, you should all be able to see the screen. So the title of my talk today is Multimodal LLMs for Smart Mobility in Africa, but the larger theme which I'd like to touch upon is about how we can harness AI and connectivity to achieve the UN SDGs. As I think most of you or many of you are aware, the SDGs were adopted a few years ago, or 10 years ago, aiming to end poverty and protect the planet, ensuring peace and prosperity for all by 2030, which is a very close deadline. I hope we can make that. Specifically, the mobility and transport related action items or goals are embedded within SDG 11, where health and well-being for all ages, which is another topic I'll be touching upon, is in SDG 3. And that particular one, SDG 3, is in fact supported in some way or another by all other goals. And how do we actually go about enabling these sustainable development goals through ICT and AI? There's there's going to be a whole that's a whole topic that we can spend a long time on, but very briefly, telecommunications and connectivity can help us do monitoring of how we are actually performing in these areas. It can help us include marginalized populations or hitherto unreached populations and reach out to them somehow and deliver services to them. And similarly, AI can help us with data analysis, prediction, optimization of our systems, and recommendations, and now very recently, generation of new solutions. And if for those of you who are interested, there's a very nice article on this in Nature Communications from a few years ago. I encourage you to see that. The reference is at the bottom of the screen. The outline of my talk today, I'm going to spend most of the time speaking about multimodal adaptation of LLMs for smart mobility in Africa. But towards the end, I'd also like to talk to you about some of the work that a couple of my PhD students are doing in user-centered design of a virtual clinic for remote areas in Africa, and also on a telesurgery system with some AI components to it. And I'm really excited about those two topics. I'll keep those toward the end. So to start off, what smart mobility and intelligent transportation, these are words that we hear quite often, but exactly how can we come up with a definition? One of the best definitions I found is from an Australian government website on the infrastructure, their infrastructure department, where they speak about mobility referring to intelligent, flexible, and sustainable approaches to transportation of different modes, of different types. Whereas intelligent transportation systems themselves are the application of ICT for the safer and more efficient management of the transport system. And these could rely upon lots of sensors and telecommunication systems at the end of the day to help users, the actual users and authorities make informed decisions about how best to use the transport system and how to make it more available to the largest segment of the population. Specifically for Africa, intelligent transportation in Africa, about a year and a half ago, in collaboration with one of my co-authors, Andrea Denziger, I wrote a white paper towards inclusive intelligent transportation in Africa, and this was funded in part by GIZ, the German Development Agency. And for those of you who are interested, I have some recommendations in there about the impact of ITS on air pollution, carbon neutrality, how electric vehicles are being used in less developed countries, also about traffic management and green city development, something which is maybe some of you have heard of. And at the end of the day, inclusivity and how we can use AI for mobility, as well as how the telecommunications companies can provide some support for efforts in these areas. So that's a recent white paper. I encourage folks to take a look at that. Also, we have in Kigali, Rwanda, where I am, we have quite a large group of people from various universities, companies, and NGOs, some of them listed over here, who have come together for a collaborative effort to form a smart mobility lab. This is us, a picture of, and you can see me in the middle over there from about March 2024. And we aim to be a platform for education, research, and also policy recommendations for not just Rwanda, but East Africa and perhaps further afield. So with this background, let me show you a couple of pictures about what's involved. So at the top left of the screen over here, you've got a rural agricultural market in the countryside somewhere in Rwanda. And you can see lots of people with vegetables. There's maybe one car parked at the back. There's lots of bicycles. People are on foot mostly. But how do the farmers get their produce to market? How do they get paid a fair price? How do they know when the bus or the truck is coming? So one of our partners, Ox Delivers, is working on that. They've got electric vehicles, but they're more broadly looking at the logistics of how to get mobility, in this case, for the farm produce of the farmers. How do you provide mobility to them? In the middle at the top, you see an electric bus by one of our other partners, Basigo. You also see a couple of screenshots over here about something to do with urban mobility on the top right. In the bottom, in the middle, a screenshot of some GTFS data put on a map by one of our other partners. And at the bottom right of the screen, you see an open source based app which ordinary people can start using to see when the next bus is going to come, or when the next, how they can maybe hail a ride or do any number of other things. So there's lots of interesting stuff happening, and this is just with the exception of the bottom right picture, I think, which is from outside Africa. All of these pictures are from Africa and Kigali. Now, remember, the title of my talk is LLMs, right, for smart mobility. But before we go into LLMs, I think we need to take a brief look, very quick look at NLP, natural language processing. And this is a slide I got from Russell and Norvig, which is a standard textbook on AI. Those of you who are in the field should be very familiar with it, and the students online should be very familiar with this one. But basically, when we talk about natural language processing, whether from the we can see, is it from the perspective of the speaker who's speaking this natural language, or the one who's listening, the hearer, the listener? If you're talking about the speaker has some intention to communicate some information to whom they're speaking with. And so they have to translate that intention into some into some actual speech, and to synthesize that with their voice, with their vocal cords and so on. This is one part of natural language. The other part, which is where much of the interesting work has been done in research fields in the last several decades, is from the listener or the hearer, or the reader for that matter. They are going to perceive some information being sent their way, maybe by sound or text or some other channel. So they're going to perceive something coming at them, and they have to analyze what the different parts of this perceived signal are. And they have to interpret that in terms of meaning, which is a semantic interpretation, but also in terms of what's the context behind this communication. And there's going to be some uncertainty exactly what is meant, and that's the case in almost all languages, if not all languages, in all communication. So there's a very important component of NLP called disambiguation. And finally, once they have understood the message being conveyed to them by the other side, they will incorporate what they have understood into their knowledge base. Now, it looks kind of technical. You can say, well, I see some grammar in there, and that's absolutely right. There's grammar, literally grammar involved with this. But when we talk about LLMs or large language models, there's a few key differences. So the differences fall into maybe 4 different categories: scope, technology complexity, the training, the data, and the real world applications. So in terms of the scope, NLP solves basically language-based tasks, like speech recognition and so on, or translation, whereas LLMs generate and understand some text based on the training that they have received, or that system has received from some huge data set. And in fact, the NLP models can be fairly simple, basically consisting of decision trees and maybe linear regression of some sort, for those of you in the computer science area, whereas LLMs rely on deep learning models, which require significant computational power and lots of data. You may have, for example, a few hundred, a few thousand rules for some grammar, depending on the kind of system you're designing in NLP. Whereas for LLMs, you're looking at easily billions of parameters that you have to update in your neural network. So the scale is totally different, and alongside that is the volume of the data. And the real world applications at the bottom of the screen, NLP looks at, for example, chatbots and virtual assistants, whereas LLMs are better suited for tasks which require human-like text. So having said that, LLMs, large language models such as GPT or generative pre-trained transformer, and I've kind of switch the normal order. Normally, you say you don't have the abbreviation outside the parentheses; you have it inside. But I've switched it around because maybe you're familiar with GPT nowadays. So LLMs such as GPT and BERT are basically advanced architectures which are used in natural language processing. Okay, so you've come up with some idea, you've developed beyond that, and you've advanced it, and you've come up with a new fancy deep neural network, which is trained on vast amounts of data with some specific objectives. And one of these objectives is to generate human-like output. LLMs also utilize something called a specific architecture, neural network-based architecture called the transformer architecture. It's very interesting. We don't have too much time to go into it, but the transformer architecture relies on something called self-attention mechanism to process the words in relation to all other words in a sentence, in a given sentence. And this attention mechanism improves the understanding of the context in that sentence. And that's really key. And there was a seminal paper on this a few years ago called Attention is All You Need. And I encourage the listeners to take a look at that if they're interested. Practically speaking, what happens when you're using an LLM? So what are the steps that go from required to go from an input prompt from a user to an output text for an LLM? So there's something initially called tokenization, where you change the input words, or you assign to them certain tokens, basically numbers. In some system, in some computer system or mathematical system, and then you can encode this bunch of tokens in a systematic manner and process that using this transformer architecture. And once you've gone through that transformer, you can use this to predict a certain output for a certain bunch of inputs. Now, it's not just necessarily going to be just one output. It could be, there's going to be a probability of the output being a number of different possibilities. So you have to maybe sample from that and perhaps choose from that. So there is some probability involved over here. And finally, you're going to be iterating over this again and again until the overall performance of your system improves to an extent which the user finds useful. So basically, the transformer, what it's doing, or any language model system, pretty much, what it's doing is it's two things. One is it's representing something, and it's also generating something. It's representing, for example, a grammar. It's representing how sentences are made up in a particular language. But not just the grammar, it's also representing the meaning that the people who have spoken that sentence or written that sentence have intended. So the representation is not just for a single task, but it's for multiple tasks. And basically what's happening is that the transformer is learning to predict the next token. Remember the parts of the sentence were broken up into tokens. So the transformer can predict the next token, but also it can predict perhaps the next whole sentence, or even the next paragraph, or the next series of paragraphs, depending on how complex things are. And things are pretty exciting and sophisticated now. So that's the bottom line. Okay, so the language models are used not just to perform a single task, but multiple tasks by learning to predict the next token or sentence, and they're representing and generating some new outputs. Now, so far we've talked about large language models and we've looked at text in a sentence. But multimodal models work with not just text, but other kinds of information. For example, images, perhaps audio clips, perhaps video. So the modality is the mode of the in which the information is encoded or it's available. Is it just available in text, or do you have other ways of representing information? That's the multimodality. So for example, if you have text to image models, you can adapt these generative models for the images. So basically what's happening is that the text in the input is guiding the output to go towards a certain kind of image. So the text prompt ends up resulting in some sort of desired image, some image output. So that's a text to image model. And in fact, a couple of years ago, some of my students over here, the bottom right over here at CMU Africa, we wrote a paper on generating African artistic styles using textual inversion. Basically text to image, and we applied it with a certain style of using African artists' work. Now, this is way before the recent excitement about Studio Ghibli and all of that. But this is many people are working on this. I'm just giving you what my students have done because I'm proud of the work that they've done here at CMU Africa. Apart from that, remember, I also want to remind you that LLMs are basically looking at a deep neural network, and there's different aspects of neural networks, different kinds of neural networks. Although the second paper, which I'm citing over here on optimizing traffic signal control for state representation using deep reinforcement learning, this is another research topic that some of my students and I have worked on. It does not involve an LLM, but it does involve those neural networks that I mentioned a few minutes ago. Now, moving from LLMs, large language models, we can move to something called visual language models. So instead of language models, we're looking at visual language models. Over here, what we're doing is we're adapting generative models for the text to interact with text and images as an input. So it's not just that you're looking at a corpus of text or a whole body of books from the library or libraries, but you're looking at text and images together. And the output, however, would normally be text. You can have different kinds of output, but normally it's text. And typically people use convolutional neural networks and vision transformers on patches of images within a larger input image. And they use it for things like logical queries or IDing objects in a picture or visual question and answering, VQA. You submit a picture of, let's say, some people sitting in a scene, and you say how many people are sitting over here, and it should be able to count. Or you can say is such and such person there, and there's going to be maybe face recognition. You can query a database of images and get a text answer back. And you can see how we can also use that for caption generation. Basically, what's happening in visual language models is that we're taking an image plus some text. We are encoding them together into some sort of a combined token of some sort, and they're concatenated together with other text embedding tokens. And that goes to the text decoder in that transformer model, which I had on the last screen. So what's happening is the image and text set combination is converted into embedding vectors, and there's different ways to do that. That's passed to a decoder transformer subsequently. And after that, you are predicting the next token, and you do that repeatedly until you address the input query. So that's it's not so far off from large language models. All you've done is you've added the capability to encode some information about an image. And you can see how we can extend this not just to an image, but also, let's say, to other forms of data like audio and so on. Now, I don't have too much time, so I want to go quickly through this, but training VLMs and multimodal models, it's really important. These are pre-training is really important because there's huge data sets containing paired text image data. This pre-training is normally done with some specific objectives and like mass modeling, captioning, and so on, that's a huge concern. But after the pre-training, there's also something called fine-tuning, where they are tuned for specific tasks, like, for example, visual question answering or image captioning, based on the application that you have in mind for this for your work. And we normally or quite often deploy reinforcement learning, perhaps from human feedback, to improve the alignment with user expectations, and also with safety, or, for example, task accuracy, depending on the application that is being considered. And this is where the reinforcement learning comes in. I had mentioned to you that we'd worked on that also. So these techniques come in at different places in a practical project all the time. For example, at the bottom of the screen, there's one bullet point I'd like to mention to you, that a visual language model might be fine-tuned on a data set of medical images and reports to, for example, assist doctors in analyzing X-rays. Now, X-rays have nothing to do necessarily with smart mobility, but that just shows to you that these techniques are actually very general. They're not specifically for they have nothing to say about the domain of the data or the information. I can apply it to that domain. I can apply it to other domains, and that's the beauty of it. So extending that a little bit further, if you're focusing down into the domain and how we can focus more on a specific domain, how it can be useful for that. So there's something called Retrieval-Augmented Generation, or RAG for short. That's an approach to incorporate up-to-date domain-specific information into large language models without retraining or fine-tuning things. Now, it takes a long time, lots of power, lots of money to train and build up LLMs. So you don't want to keep doing that with whenever a new piece of information comes available to you. But what you want to do is you want to be able to update your LLM somehow. And so RAG allows you to do that. And there's different techniques in it, such as vector and full text or hybrid search. We don't need to get into that right now. But basically what's happening is that RAG ensures that LLM outputs more closely match some trusted information. Okay, so the trusted information, it's correct. It's not something probabilistic and maybe right, maybe wrong, maybe hallucinating, nothing of that sort. It's trusted information. You want to tie it closely to that. And so the outputs you're going to have more confidence in the outputs. And that's something which a real practical system should give the user some confidence that the answers are correct. Now, let's extend this finally and come to smart mobility. So it would be ideal to customize some application for multimodal large language models, MLLM for short, for smart mobility. And how do we do that? How do we customize things? We customize it with local current data, like local and current data, such as schedules, for example, regional language safety, construction alerts, perhaps the kind of GPS traces that Thomas spoke of in the introduction, and maybe audio alerts of some sort. All sorts of different modalities can come into this, and that information is available, but it's perhaps not stored in some central area. So we have to go out and look for it and basically use it. There's been some really good recent related work around this, and a couple of papers I'm just going to put up on the screen. Elastic modality for adaptation, multimodal embedded AI, really embodied AI, that came out in December 23, I believe. There's also a more recent paper from December 24 on multimodal LLMs for intelligent transportation systems. And so there's lots of recent interest in this area, and we hope to extend it somehow. Now, specifically for Africa, there's challenges in LLMs, and they boil down to 2 or 3 things: computational resources. MLLMs require lots of GPU time for training and inference, so that's a cost that we have to fund somehow. There's also real-time processing that could be done in perhaps with lightweight models like mobile VLM, That's something else to look at. But fundamentally, and most importantly, in my opinion, is actually the data quality. We have to get our hands and curate, find and clean up and make usable some high quality, diverse data sets to avoid biases. And biases over here, I mean, you're not showing the actual conditions of the roads in the areas that this system will be deployed. What are the people and economic strata who are going to be using these systems or these solutions? What kind of unique vehicles are available there? What's expected while driving or walking on the roadside? What language is used? What kind of weather is there? All of these things are details which are quite often missing from data sets from, let's say, the global north or elsewhere. So customized, high quality data is key. And beyond that, we have to look at things like safety and reliability, having robust designs, maybe having backup systems, and so on. Also, there's ethical concerns around privacy also. So here are a few pictures from Africa. I got this off the internet just a few hours ago. We've got a scene at the bottom left from Cape Town, South Africa. It looks, fairly developed, so not too different from what you might find elsewhere. But Africa, the rest of Africa is very different. If you jump over to the top left over there, that's a scene, I believe, if I'm not mistaken, from somewhere in West Africa. Maybe Cameroon, if I'm not sure exactly, but the road is very different. The condition of the road is different. There's lots more motorcycles. We have to be aware of that for any system here. If you go to the top middle, if you go to countryside, the roads are narrow, and there may be livestock. If you go to the top right, in Cairo, Egypt, you might find people with some strange tricycle. I've never seen that before, but will your automated LLM be able to detect that and say something about it, or warn drivers about it, or warn that rider about other things in the roadway? And all of these are in the daylight, but what happens at night? And what happens when it's raining? So the data sets that we want to get our hands on or collect are going to be quite diverse and quite rich for a wide variety of situations. In terms of the data itself, there may be, if you go to a European country, you might find this table of with the schedule of buses. But if you go to Nyabugogo in Kigali in the top left, I've actually walked into one of those buildings. There was no information. I had to talk to somebody and get some information about the next bus to Kampala, for example. The buses are great, very beautiful, but where's the information about the schedule? I don't know. Can we look at traces? This trace, I believe, is from Johannesburg of some taxi down there. So can we use that instead and make sense of things for our system? So what we propose to do is a multimodal LLM for smart mobility, and which has three components: data acquisition, curation, model adaptation, including RAG, and deployment, some sort of deployment interface with a web-based application. That's our basic proposal. Some of my students and I would like to get started on this. We've got some initial funding, and we need some additional resources to get going on that. So there's many considerations over here. Maybe I can keep this for the quick Q&A, but there's open source tools and frameworks and test beds and standards that we have to consider while coming up with our system. The most critical thing, again, is that local data. Okay. So with that, I'm skipping a few slides here. I'll come back later, but we mentioned that we want to look at a few cities in Africa, including Kigali on the right, Nairobi in the middle here, and Lagos on the left. There's different kinds of data available for each of these different cities. Some we don't have it yet. And as you can tell, the red is a warning, lots of congestion in all these places. How do we get around this? Kigali is a fairly small city, fairly well regulated, so that's going to give us some ideas. Nairobi's central business district is a little bit better. It's compact, but also it has some problems heavy traffic, lots of congestion. Lagos is huge and sprawling. So there's different kinds of cities across Africa we like to look at, and that's not even looking at the rural areas just yet. Some references over here for you. Let me quickly, I'm going to skip this recap and come back in the Q&A. I'd like to spend some time on my next topic here, which is, and I'm shifting gears here. I'm moving now for smart mobility to telemedicine. And the connection over here is that we're still using ICT, telecommunications, and AI to provide solutions which will help us meet the UN SDGs. In this case, specifically, not in terms of urban design and urban transportation, but rather in terms of health. How do we leverage the same kind of tools, ICT and AI, to help us deliver healthcare to remote, rural, and underserved areas in Africa? So one of my students, I'm her co-advisor, has been working at UCT, University of Cape Town in South Africa, on user-centered design of a primary care virtual clinic for remote, rural, and underserved areas. And these are some of the partnering institutions. Basically, the number of physicians per 1,000 people in sub-Saharan Africa is negligible. Okay, it's like 0.1 or something. Whereas in the world average is 1.8 per 1,000. And if you go to developed countries in Europe or the UK, it's like 5 or above. So, and these are statistics from the World Health Organization from a few years ago. I don't think it's much better right now. So there's a huge clinical need to provide physicians to take a look at patients in these remote areas. So there's a limited number of doctors, inefficient primary healthcare services, and hence people just don't even consider going to the doctor. And hence there's also perhaps higher disease burden in those countries. So one idea is to use virtual clinics and user-centered design, where we kind of analyze what is the need of particular communities. And these could be rural underserved communities. There could be urban underserved communities, maybe in a tough part of town where people are not, the number of hospitals is few. So we want to understand the actual context of the use or the requirements for healthcare for those populations. We'll specify those user requirements, design some solutions, evaluate, make a system and evaluate against that. This is actually a software development process, if you think about it. I mean, those of you who are software developers will recognize it as that. But it's a similar technique. We want to have a user-centered design. The particular application happens to be telemedicine. And Abby has come up with, that's her in the middle over there in the screenshot. She's come up with a virtual clinic where the patient has some information about him or her, some of it gathered from actual physical devices like a glucometer or a digital dermoscope or otoscope, which is available at low cost in these clinics, these remote clinics, where we have a partner who has been trained, a nurse, perhaps nurse, and then that information is transmitted over some telecommunication link to a doctor who's sitting remotely in some place in a healthcare provider area. And there's questions about what kind of data should be gathered, what kind of health records should be there, what's the privacy of those things. But this has been pretty successful. We've tested it out in a remote, underserved area in Cape Town itself, but also in a remote area in the Western Cape or Eastern Cape. I'm not sure exactly which province it comes under, in a desert area where there's only literally one clinic and one nurse. So this is developed virtual clinic system. Here are some of our publications on that. Very interesting stuff. I encourage those of you who are interested to take a look at some of these publications. We've also done some work on the last reference over here on benchmarking Xihosa automatic speech recognition and machine translation for digital health provision. And so that's a AI component where we're doing some machine translation. It's not LLMs, but it's machine translation, and that's actually very useful because many people in these areas may not speak English or Afrikaans, but they are describing their medical condition somehow, and that has to be translated not just for the nurse. The nurse may or may not know their language, their local language, and South Africa has many, but also how does it translate? How does that description translate to something, to a medical term, which is understood by doctors anywhere? So there's lots of interesting stuff over here. We've also looked at the capability of 3G, 4G, and 5G networks to deliver the virtual clinics and optimized it for those networks. And we are developing deployment on 5G. So that project is almost coming to an end in the next 6 months. But another project has just gotten started with another student on a laparoscopic surgical telementoring with automatic bleeding monitoring. And this is being undertaken by another one of my students in Cape Town called Prosper Magara. He's from Zimbabwe, actually. And he's recently proposed this integrated surgical telementoring system with automatic bleeding monitoring and warning to support laparoscopic surgery. So just to give you a background, laparoscopic surgery is a minimally invasive surgery where small incisions are made in the abdomen, and a couple of instruments are inserted there, and carbon dioxide gas is pumped in to inflate the abdomen so that there's space to work a little bit. And there's like a camera in there, and the image from that is displayed on a monitor. I've actually handled one of these things in a test center here in Kigali. And there are some specialized surgical operation tools for operation. That's what it might look like. Okay, this is obviously not a real picture, but like stylized picture. So it takes a lot of training for this. And so the way it normally happens is that there's trained medical doctors who are surgeons, like trained surgeons, and then they go through some additional training to do laparoscopic surgery. The problem is that the number of doctors to begin with in Africa is low, and the number of doctors who can mentor junior doctors is even less. So can we have a trained surgeon sitting in Kigali help a aspiring or a new surgeon sitting in someplace in Tanzania, for example? And we proposed, yes, there's ways to do it. In fact, another one of my collaborators at ERCAD is doing precisely that. And there's certain challenges in laparoscopic surgery. There's limited, like we said, limited access to experts. Systems lack worldview visualization of the trainee doctor's posture and how they're using the tool. And one of the third point over here, that during the operation, bleeding, there's a lot of, there's possibility there's bleeding apart from due to the incision, and it could suddenly get out of hand. In fact, bleeding accounts for maybe 23% of adverse events, but the real-time bleeding monitoring is almost non-existent. And so there's a lot of pressure on the trainee surgeon to keep an eye on not just what they're operating on, but also on the peripheral view in that, not peripheral, but I guess the side view of theirs in their monitor showing the scene inside the abdomen. So there's a lot of pressure for a doctor in case of a bleeding occurring. So can we come up with a system which detects that bleeding or the onset of bleeding and warns the doctor ahead of time, so that if there is such, such an event, they can take immediate action and wrap things up quickly. So we have a proposed solution where we use some peer-to-peer real-time communications via web RTC over 5G network. There'll be dual video feeds. There'll be an AI-enabled blood monitoring system and warning system for prediction, detection, source tracking, and rate estimation, as well as the cumulative loss of the blood. And there's we'll also be displaying relevant information on the monitors of the remote mentor and the local surgeon through something called transparent illustration. And this is the basic system diagram for our system, and we are using an NVIDIA Jetson with a DeepStream SDK. So very quickly, what the evaluation setup is going to look like is something like this. We have a remote Mentee setup where this is the main block in the middle of the screen here, where we've got this is actually this part here. It says A, remote Mentee setup, panel A. It's a artificial bleeding model, so it's not a human being or an animal at this stage just yet, but we're going to be looking at the screen and simulating the bleeding initially, and inserting needles through this device on the bottom left, and mimicking this this setup. Now, this is for training, right? This is not an actual deployment picture, but this simulates very closely what will be visible to an actual trainee surgeon and the tools available to them when they're doing laparoscopic surgery. So that information, the visual information plus any local AI detection that we've done, is sent over this communication infrastructure to a remote mentor somewhere, and they're looking at this on their PC or laptop. The performance metrics of concern will be latency, detection time, and as well as the user satisfaction. Lots of interesting stuff here. Let me stop because we're out of time, but I'd love to go into more details on this. Yeah, so let me just stop here and open it up for questions.
Thank you very much, Ahmed. I think while we wait for questions from the audience, by the way, audience can put their questions in the neural network, and we should be able to get some time from Ahmed before he runs away. But I have some questions myself. So, you know, both these use cases, we call them as use cases, and they are both very interesting for us because there are certain characteristics which you explained right from beginning. But by the way, thank you very much for really laying out, starting from NLP onwards to the transformers, and then coming to the use case, right? It's a really good lecture that we've got today. So from both those use cases, there are certain characteristics that we try to derive, and those are really important lessons for us. However, I think you rightly mentioned the data set preparation is the key. I want to ask you upfront, how do you collect this data set? Do you need labeling, or do you use some kind of pre-trained models to segment or try to analyze them using models? The reason I'm asking is that IQ has several initiatives which are looking at collecting, regionally relevant data as part of AI for good. We try to create regional knowledge bases, RAG, as you rightly mentioned. It's a really valuable initiative for us. So, how do you propose to collect the data set?
Okay, so there are some open source or readily available data sets, but not really suited for Africa. So that's a starting point for maybe a very nice road somewhere, which is very nicely controlled. There are, let me just quickly go over here. There, one of the slides mentions if you look at the test beds in this important consideration slide in the third bullet point, test beds like Carla, BDDK, BDD100K, and Ushahidi, some of them have some data sets, but they're not really suited. So what we want to do is we want to go to the next step. I think the test beds are good as a starting point, but we'll probably go around collecting data from local boda drivers or local motor drivers, as we call them in Rwanda. I myself have an electric vehicle with a bunch of cameras. I'm sharing with some colleagues. So we have some videos that we can perhaps use. We might reach out to operators like Yego in Rwanda and others in other countries. In Rwanda, in particular, there's the Rwanda Utility Regulatory Authority, which actually has a mandate to collect data from the different public transportation operators. We might approach them. There's some rules and some hoops we have to jump through. So there's some data which is available. There's some regulations that we have to meet in order to get or collect that data. If we are able to partner with, as you mentioned, other folks in the region where the standards are perhaps a little bit easier than in Rwanda, we'd love to maybe partner with them. So these are some of the considerations that we have right now.
Very good. Yeah, I think this is a longer conversation. I think we should catch up again on this topic. We are very interested to do this. And then slide 34. If you go to slide 34, I have a really specific note there. Slide 34 is
my number has disappeared. Is this number 34?
No, it has this patient. There is an
30, 31, 32, 33, 34. This one, yeah.
Yeah, that one, yeah. So this one is really interesting. I mean, this is our dream. I mean, this is an SDO's dream, a standard maker's dream. I mean, see, look at the number of lines you have. Look at the number of interfaces. They all translate to interfaces for us. So it's really a standard maker's dream, this particular slide. The problem here is that there is health data from sensors, then you have medical devices component, data processing component, there is a health provider component. What do you see as the moving parts? I mean, there are interoperable, domain-specific, AI-native interfaces. That's what we would like to really focus upon, these interfaces should be interoperable, they should be domain-specific. At the same time, I think given the background of your talk, given your previous slides, I would say that these interfaces one day will become AI native. What is your comment?
So in some ways, the virtual clinic system has the luxury, if you want to call it that, of some work already having been done in regulations like called FHIR. FHIR. It's a health information records standard, and in fact, the student is qualified to not just work with that, but to teach it to others. So there are already some regulations about how healthcare-related data should be stored in electronic health records or conveyed, or what kind of security, what kind of privacy there should be. So far, we've not really seen too much on AI. Regulations around AI in those records beyond the larger privacy, but people are moving in that direction. One of the things is, and I think it will remain the case, is that ultimately, who is responsible for something going wrong, right? And so there has to be not a human in the loop, but a doctor in the loop. Right? There has to be a doctor in the loop somewhere, and there's going to be recommendations. But at the end of the day, do these recommendations fit into the clinical workflow which the doctors and nurses and practitioners and healthcare workers are using? And so I think we'll see more guidance around that, more guidance around maybe safety procedures in case something goes wrong. We're not there yet, but I think we'll probably see those additional recommendations coming in. Apart from air travel, I think healthcare is one of the more regulated activities. So we'll see more of that. Having said that, I was also recently at a conference here in Kigali on medical education, and there was a big section on how AI can be incorporated into medical education, not just in medicine, but in medical education, because quite a few of the physicians who are being trained are going through a very rigorous program. There's hardly enough time for them to study about AI and how AI can be adapted. It is only interdisciplinary teams after people graduate, maybe a doctor takes an interest in AI and how AI can improve his or her workflow in their hospital. And at that point, they assemble a team if they have the right funding, and that team then does something amazing. We're seeing more and more of that happening. I was very pleased to see that there were a large number of deans at this conference, and there is a desire to have this kind of guidance and regulation. Right now, it's a little bit haphazard from what I've seen.
Thank you very much. Thank you very much. I believe this is another deep topic which we may not be able to cover in a few minutes. Anyways, I think there is an interesting question that Blessed is asking about transferability of multimodal models, especially across. I mean, he's asking about African cities, but I asked the same question across Africa, Asia, Europe, and such countries. You showed this picture of that tricycle. We see it here. We see it in many cities here, and we had one AI machine learning challenge where we looked at collecting such pictures. Yeah, this one. Yeah, thank you. Yeah, so this kind of images, collecting such images was one of the machine learning challenges that ITU did as well for local transportation. So I think the transferability of multimodal models is a very important question. It's not only for Africa, but also for rest of the world as well. What is your opinion? How do you comment on the possibility of this generalization and transferability of models?
So, one of the recent papers and which I mentioned in this area is about the elasticity or elastic adaptability somehow. You may want to switch from one mode to another mode at short notice. So we could get information about certain behaviors in one city where people are using their voice more often to alert each other. We grab that. Is there like a wrapper in our system which allows us to pick that up quickly? And if we've learned that in one location, can we then transfer that knowledge to another location? I think yes, we can. But at the end of the day, there's going to be a customization of some sort going on. Or for example, you may have how to deal with a narrow road with animals on it. Perhaps you don't have the same kind of cow, but if you have a cow, you got a cow. How do you avoid that? But I think there is some room for transferability of knowledge gained in one geographic location to another, but that final customization is going to be very critical, in fact. But definitely that's something that's a good question, and it kind of mirrors some of the stuff that we hear about federated learning, where you may have a different population or different kind of set of devices or some kind of features for some problem in one area. You learned about that in that geographic area, but can you then apply it elsewhere, or can you extend your model, your overall model to be robust in case it encounters that situation elsewhere? So I think there is some room for that. Exactly how it's done is going to probably lead to many interesting projects.
Thank you very much. I was wondering what does that elasticity means, and I've noted it down to read that reference that you showed. Yeah, thank you for explaining. I think the deep reinforcement learning part, I believe you just now touched upon that as well. But the other part that you had in your slides, I think somewhere, and you also mentioned it in the context of this medical use case as well. So can you explain a little bit more about the role of this reinforcement learning in your work?
So let's see. I think I mentioned it in one of the places I mentioned it was in the medical area right here.
I think
So
you had your one of your papers, one of your previous work was based upon deep
right,
reinforcement learning. Yeah.
right. So you're absolutely right. There was one further up about the reinforcement learning for traffic modeling and traffic management. But it could also be used in a case like this. In both cases, what we're looking at is the proper behavior which you want to see coming from your system, and you want to model, let's say, the road network, or you want to model the surgical operation area in a way that good practices are rewarded and bad practices are negatively impacted. So the reinforcement learning is reinforcing positive behavior by the trainee nurse or by the trainee physician, the trainee surgeon, or it is reinforcing positive behavior by an algorithm which is timing the traffic lights in a way such that the traffic is more efficient. So such behavior is going to be rewarded, and that's being reinforced. Whereas, and that's rewarded against obviously some objective function. The objective function in the case of the traffic would be more efficient, safe traffic. Objective function over here would be not to cause bleeding, not to cause some other harm to the patient. So behaviors which are positive will be rewarded. Behaviors which are negative will be negatively impacted, whether it's by a human surgeon or whether it's by the ordering of traffic lights. That's the basic idea. Obviously, we can get into a lot more detail than that, but that's the basic idea for our viewers. Yeah.
Thank you very much. Yeah, I think it's really interesting work. I have one question on the tokenization parts you mentioned. I think in one of your slides, you did talk about multimodal data sets. And I was trying to understand how tokenization applies to these different models. Of course, tokenization typically is handled in case of text, but probably you have similar concepts for images, something like segmentation, audio, video, they all go through this segmentation, right? So, in case of, have you looked at this? Yeah, exactly, this slide. Yeah. So, in case of this multimodal data, once you somehow segment it or tokenize it, what kind of role does this modality plays in it? Is there when you even when you're training, even when you're collecting the data set, what kind of should we still worry about the modality, or should we look at the relationship between the tokens, as you mentioned in the case of transformers? What is the role of modality after tokenization or segmentation?
Okay, so that's actually a great question. In this particular example, I've got some image data or image patch, which is encoded and it's tokenized, and it's concatenated with another part of that larger token from the text embedding. There's different ways to do that. One of them, one of the more familiar ones you may know, is called vector quantization and auto encoding. That's where you have the numbers basically, and you're dealing with numbers, okay? And then that number is representing some location in a large dimensional space. And if you come up with some new image, which is similar to the first one, it's going to be somewhere in that area somehow. That's one way to basically visualize it. There's another approach called clip encoding. You may have heard of that, clip encoding and so on, where the model is learning directly about the position within this larger search space of the concept of let's say the cat in the image and the word cat. So it's not the numbers, but rather it's looking at if someone asks me, or if the query is about a cat in the image, I'm going to look in this part of that knowledge representation space. And in many cases that works better than just looking at the actual numbers, because you're not worried about the numbers. You're looking at the area of the search, and you may still be doing some search subsequently, but it's going to get you to the location faster. So that's like a very high level answer, but I hope that you're able to understand that we are encoding in a very high dimensional search space information about both the text and the image, or any other mode with audio or video parts. We have to be careful in the video about the alignment. But so what is a better approach? I think it'll depend on the application. In some applications, it might be that you just want to go with the numbers, the VQ vector quantization approach. In some other cases, especially for video, it might be better for the clip. So it depends. And there's others also, not just these two, but there's others also.
Thank you very much.
Yeah.
Thank you very much. I think it's a great pleasure talking to you again, Hamad. And thank you for the very patient, wonderful lecture that we got today. We hope to engage with you. In fact, Thomas is here. We will explain about our summit and workshops. It would be a pleasure to talk a little bit more on that sidelines. Thank you very much. Back to you, Thomas.
Thank you, Vishnu.
Thanks a lot, Vishnu, for moderating the Q&A. At this point, I would like to thank everyone for joining today's session, but more specifically, I would like to thank Professor Biabani for making time and presenting these interesting insights, especially on your research in large language models and how they can be transformed in specific domains, especially in mobility. But also I'd like to encourage everyone to visit our website, AI for Good, where you can find information about our upcoming summit, which is in July 2025 in Parexpo, Geneva. We also have a lot of webinars, a lot of sessions, so please join us on the neural network if you have not done so. But also at the same time, you can find many other sessions that we are hosting. So from me, I would like to thank everyone and wish you a very good day. This is the end of our webinar. Have a great day. Bye.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.